And welcome to this recording for chapter 42. Chapter 42 deals basically with molecules and solids. So we're going to introduce basically the bonding basically between different atoms to form this different structures. So the first one, after we basically discovered the atom, the hydrogen atom, and then went through the periodic table basically, and we have a full development for that theory, now is basically when we put more atoms together. There are several kinds of bonding, okay, between different atoms. There are four types basically that we're going to be mentioning in here, and then when it comes to solids we will have another type of bonding actually called the metallic bonding, and that is due to the electron clouds basically that is shared between the different atoms in the case of conductors, in the case of metals. So the first one is of course ionic bonding. And in this case, basically, you have two kinds of atoms. Typically, typical example is the alkali with the halogens. Case in point, for example, you have sodium that can lose an electron if you provide it and become ionized. Actually, one of the 2s electron, the 2s electron. There is only one there. So you're going to lose it at the expense of 5.138 electron volt. So you need this amount of energy. If you do, then you're going to end up with an ion for sodium with short of 1 electron. On the other hand, chlorine, which is a halogen, will release an amount of energy 3.613 electron volt, and capturing that electron. So basically it will settle so that its last shell, the 2p shell, will be now saturated, gaining that extra electron and become a negatively ionized. Okay, it has an affinity with this much an energy for electrons. Basically it's going to release that much energy, so it's going to release it to the sodium. So it's still, the equation in here is still deficient, because if you subtract the 2, you're going to require an amount of energy in addition to that is 1.52 13 minus 8, 5.25 electron volts. So you need, really you're not if that's all you do, you don't have enough energy to mix the two. Here is the deal. Because you have now a negative charge, which is this ion, and a positive charge, which is this ion, they naturally attract one another, and they will keep on attracting one another according to Coulomb's law, except at some point they cannot really attract too close to one another, because there will be repulsion due to their outer shells basically that are negatively charged, so they repel one another. The model for that is, and I think we did that in one of the problems in the past, is the following. Basically there is an attraction at far away distances, so this is the distance r. So there is an attraction where the energy is negative, but then as you get closer and closer, because of the Pauli exclusion principle, it's repulsion. So at some point the energy levels off at an equilibrium point between these two ions at a nominal distance in here, which is called R0, usually referred to as R0. For the case of sodium in here and chlorine, the energy required is actually has a negative value of 5.7 electron volt. So as these two come together, we have more than fully accounted for this amount of energy that needs to be compensated for to ionize the sodium in here, because we have a negative 5.7. As a matter of fact, the excess energy in this case for this interaction will be what, if we add the 2, it's going to be an amount that is a net value of 4.2 something, okay, 4.2 electron volt. Here is the deal. This amount of energy now is released by this molecule and to form itself. However, of course, because of thermal agitation, there is a little bit less energy available for that because this molecule keep on moving. So if you do the calculation, include the temperature into account, this is not the full amount of energy that is released because these two are in other words, it's a stable configuration, and this is everyday salt. So this is an example of ionic bond, and it's typical, like I said, between alkalis and halogens. So this is one way of doing the bonding. And some other ways of doing the bonding is where the electrons are not fully released from one atom to the other one, but rather they are shared. In this case, we call it the covalent bonding. Both these two types of bonding to form molecules require an amount of energy usually between 1 and basically 5 electron volt. Okay? Remember, to ionize, for example, the hydrogen atom require a lot of energy. So this is the case of the sodium because it's in the 2s, but for the case of the hydrogen, it was like something like 13 or 14, 13.6 to be more exact, electron volt. So but this is basically to form both the covalent and the ionic bonding, and this is the amount of energy associated with this kind of interaction. In addition to that, there is a third type of bonding, and this is to a dipole-induced dipole interaction. So basically, what happened in this case is, as the molecules form, the electrons, they are not exactly shared in the middle, but somewhere closer to one atom than the other. One of them still has a higher affinity for electrons than the other. So there is a net charge on one side, and lack thereof, negative charge on the other side. Okay, so this is a positive and the other one is negative. So now you have an electrical dipole, which will induce another dipole in the next nearest neighbor, and that, in a sense, is what is responsible for this so-called van der Waals interaction. So this is the van der Waals bond, and let me write the name in here. This is typically a lot weaker energy. It's very easily broken. The case in point is the case of water, for example, because water is an example of a dipolar structure. And here, soaps also are typical of that because of the fact that they attach themselves to dirt. So actually, this is the water that does that. Okay, so this is the amount of energy associated with this kind of interaction, so it's a lot weaker than the first two. And there is a fourth one in here, as I mentioned before. Those are the four typical bonding for the case of this is an organic chemistry mainly, and this is the hydrogen bonds. And the hydrogen bond is a little bit more energetic than the van der Waals, and again it's about 0.8 electron volt, where the hydrogen in this case is shared between different groups of molecules to form long chains of molecules. So this is typical of organic chemistry. Now this is basically the type of thing, the type of attractions that we will have. Let's try to model this to see how it's going to work, because again we need to do some problems in here. One way, for example, to look at a molecule, for example, to take a case of a diatomic molecule. Okay, so it's usually made up of an element M1 and of another element of type mass 2, an atom and another atom. And in this case, because of the way that this molecule is this way basically structured, we can actually work out similar problems, or at least an approximation for Schrodinger's equation. And one of the things that is added, in other words, in here to this equation is the different kinds of rotation modes that this rotation energies that this system will have. Okay, obviously any rotation is associated with an angular momentum, and if we do quantization, the angular momentum in here is going to be expressed by L. Okay, so this is the angular momentum. Its projection along some direction is going to be m. Okay, so we will have some problems with that, okay, associated with that. Another type of interaction is, of course, the vibration of the molecule itself, which you can approximate it as some sort of a harmonic oscillator. and where this is the K for the atom, and in this case this is M2 and this is M1, and then you can solve for the problem for this 2 in here. And again, the energy in here in this case is going to be that of a harmonic oscillator. And we have seen that when we did chapter 40 actually, and we also did this in chapter 41 and 40. So the total energy in this case is, this is going to be characterized by an integer n, this is characterized by an integer L, where the energy in this case for the entire molecule is somehow related to both quantum numbers n and L, where for the vibrations, for the rotation is going to be expressed by this quantity in this case, namely that of the angular momentum divided by, again in this case it's not going to be mass times the distance squared. We really need the moment of inertia. Typically the moment of inertia is taken about some sort of a center of mass in here, and we're going to address this two-body problem to find how that momentum would look like. Plus again, the quantization of the energy due to vibration, which is n plus 1/2 times h bar omega, and h bar omega is that constant again divided by the reduced mass m in this case. So what is this I and this mr coming from? Let's quickly look at this problem. This problem basically can be represented as follows: as if you have a center of rotation somewhere in here, and you have a mass that has the reduced mass of the two systems, and now that one is actually spinning or going around this circle at a radius which is equal to this distance r0, okay, between the two masses. So this is r0. Similarly, this problem could be resolved into a mass attached to a spring system, where in this case this is again the reduced mass, and the K is the same K as represented in that diagram. So the K, you're wondering what is that? It's the restoring force basically, so that the molecule stays in equilibrium. So this is due to the thermal agitation or whatever excited the molecule to take it out of its spectrum. Again, when you do spectral analysis, you're going to get different frequencies that correspond to, among other things, to this kind of transition between two different energy levels, whether in the L or whether in the N, basically for this structure. So I mentioned something about the reduced mass. So where is that coming from? Let's take, for example, the case of rotation and see how that moment of inertia around the center of mass really is going to be, in this case, that of the mass, the reduced mass, times r0 squared. Okay, so r in this case is the reduced mass. mr is equal to the product of the two masses divided by the sum of the two masses. So that is exactly what the reduced mass is. So let's see how that, where that expression comes from. If I go back into the picture again that I drew earlier, so I have two masses in here. This is M1, let's call this one M2, and this is M1 because I like to refer to M1 being positive. So this is the center of mass somewhere in there. Obviously in the case of the proton and the electron, if I'm looking at just the atom itself, the center is very, very much near the proton, but in this case you have two atoms, so the center of mass could very well be between the two atoms, okay? Between the two atoms, yes, to form the molecule. So this is R1, this is R2, in the center of mass reference frame, because we want to calculate the moment of inertia in that frame, okay? Now, the vector connecting between M2 and M1, as I said before, it's this vector. It's clearly that R0 is equal to, from the geometry, R1 minus R2. Okay? Because the vectors, this is two vectors in here. And the center of mass, in the center of mass reference frame is at position 0. It never changed, because this is the expression in general for the center of mass, M1 R1 plus M2 R2 divided by the sum of the masses. Well, the only difference in this case, this expression is true no matter which reference frame you're looking at, but in the case of the center of mass frame, this is the origin. Of coordinates basically 0, 0. Okay, so in this case this must be a 0 vector. So this immediately gives me an expression relationship between R2 and R1, namely R2 as a vector is equal to minus M1 over M2 times R1. Okay, so now Obviously, this expression for R naught now can be rewritten as in terms of R1. R naught, remember, is R1 minus R2, and R2 is a minus, so it's a minus times minus becomes a positive over M1 over M2 times R1. And now take R1 as a common factor, and the common denominator is M2, so this is M1 plus M2 times R1. In other words, R1 is simply equal to M2 over M1 plus M2 times R0. Okay, that's equation 1. That is an important one in calculating the moment of inertia, because the moment of inertia is just the sum of the two momenta of inertia with respect to the center of mass. So in this case, that's one quantity. I need the other two, R2. R2 for R2, I just have to multiply this expression by M1, negative M1 that is, and divide by M2. When I divide by M2, M2 cancels, so I will be left with just negative M1. So R2 is negative M1 over M1 plus M2. This is a 2 times R0. Okay. And then you're wondering, what does that minus mean? It's only just my choice of direction, that's all, because R2 is clearly pointing in the opposite direction to where R0 is pointing. Anyway, so it should not matter, because we're going to square this quantity to find the moment of inertia. So the moment of inertia with respect to the center of mass of these two masses, I'm going to drop the COM because I know it's with respect to the center of mass, so it's just I. If you care, I mean, if you just... So this is how I'm defining I in this case. It's just M1 R1 squared plus M2 R2 squared. I have 2 point particles basically, and I'm calculating their moment of inertia with respect to a point that is between them. So it's just, this is the sum. When I square this quantity and multiply by M1, it's going to give me M1. Remember, in R1 I have M2 in the numerator, so it's going to be M2 squared over M1 plus M2 squared times R0. And that's the whole purpose of that exercise, is to find that expression in terms of R0. Okay, squared plus, now this is what I was talking about in here. When I square this quantity, it's not going to matter in this case, it's going to be positive, times M2. So I have an M1 in the numerator, so when I square it, it's going to be M1 squared. So I have an M2 times M1 squared over M1 plus M2 squared times R0 squared. They are almost identical with the exception I have here M1 times M2 squared, and in here I have M2 times M1 squared. When I'm going to take M1 times M2 as a common factor, so I will be left with an M2 plus M1 divided by M1 plus M2 squared. So one of those squared in the denominator will cancel the numerator, and all I'm left with is just M1 M2 over M1 plus M2 times R0 squared, which is just how I define the reduced mass times R0 squared. So this is an important result, that in this expression in here, all I'm saying in here is that in the center of mass reference frame, the system of the actual atoms to form this molecule behave just like this, as if it's just one particle of mass reduced mass, and it has that basically oscillations, if you want to call it rotation, I should say, in this case with respect to that distance. Similar treatment will yield to the same answer in this case for this. As a matter of fact, you can show that it's actually the same thing in here for this system in here. Anyway, so we have the expression for I, where we're going to sub it in there. I already wrote it in terms of for the total energy for the system, and also that includes also the quantity that has to do with the rotation, with the oscillation. So this is the oscillation, this is the rotation for a molecule. Again, you're going to have a lot of homework problems and stuff assigned to this one, and all you have to do is calculate transitions between the different energy levels, for example, with different angular momentum numbers. Okay, and there you're going to find the specific frequencies that correspond to this ones in here. Look, it's going to be much higher, much longer wavelength. Actually, it's going to be in the infrared region, so that you guys are wondering if we're going to get anything in the micrometer. No, you're going to get things usually. Obviously, visible light is not even in the micrometer. It's several hundred nanometers, so it's still it's probably tenth or less than that. So in terms of tenth of a micrometer or less than that for the case of the visible light. But these frequencies in here, they're all going to be in the infrared, sometimes even in the microwave region. Okay, so when you're doing calculation, you have to pay attention to the wavelengths that you're going to come up with, or the energy, the frequencies that you're going to end up with. Anyway, so we're going to do problems in here, and hopefully that will clarify some of these things and how we apply them. How molecules form, basically atoms in this case, how molecules form solids in this case, how they organize to form the solids, is another problem altogether. And sometimes they have a crystalline structure, sometimes they don't have a crystalline structure. In the case of a crystalline structure, we have so many ways for them when they are packed together. And at least I'm going to list in here about 3 or 4 of them. The first one is the simple cubic structure. Okay, typically this is of the same atom, same molecule, same atom, in this case of solid. Okay, provided that there are no impurities. In this case, this is a simple cubic crystal. Okay, in some cases, like for example in the case of sodium chloride, you have what is known as an FCC system. So basically you have face central cubic face-centered cubic system or crystal. So you have a different molecule in here in the face. So this is the face, the up face, and inside in here you have a different molecule. And it alternates. Actually, if you look at the case of the sodium chloride, sometimes the sodium will be sitting in here and the chlorine will be here. Of course, there are ions. And or the other way around, for example, depending on how you look at it, it could be the other way around. Okay, so that is basically the face-centered. If you do material science, this is a big topic where you can spend a lot of time actually in trying to understand the different kind of configurations and what that means in terms of the basically the different physical and chemical properties, especially physical properties. Okay. Now, in terms of another one that you can have in here is the body-centered system, in a sense that inside, I'm just trying to draw in here some simple shapes in here for the crystal. So this is the front side, or at least one side of it. If you connect this one, to the diagonally opposed to it, this one to the diagonally opposed to it, this one diagonally opposed to it, there is another one that is opposed to this one from the other side that is not showing in here where the other type of atom is. Again, you don't have to really necessarily have it of a different type, but at least this is one way of looking at it in this case. Okay, so this is so this is a body-centered cubic crystal. And the last one I'm going to mention in here is the hexagonal closed packed system. This is actually you have a hexagon in here, and the motif in here, or the cell that repeats, has this structure in it in here. So you have 1, 2, 3, 4, 5, and 6, and in the center of it you have another one in here, and this repeats up and down. Okay, so this is the hexagonal close packed. We may do something in here in terms of homework and work problems, but I don't know honestly at this point. I didn't decide yet onto this kind of things because we have quite a few things to work on. Okay, what's going on when you have different molecules getting together now, or at least, yeah, molecules getting together now to form a solid? This is the situation. Okay, remember, in a single atom you have different energy levels, and that is true also actually of molecules too. Okay, you have different energy. We saw that at least a few minutes ago. Now, as they come closer from another, the electrons from this electronic structure and this electronic structure become closer and closer from one another. So what they do in this case, the energy levels start to collide with one another, and the clouds themselves start to deform, and they form basically gaps between them. So you have now, at some points, at far away, they have clear energy levels. Once you have them close from one another, at that point, each and every one of this energy levels starts to split into different smaller energy levels, because now they are very close from one another. As they get very close from one another, the exclusion principle in this case becomes at work and does not really let them come any closer. But because, again, you have reached now the stability. So what you end up with in this case, you end up with energy levels where you have a bunch of this is a huge number, of course, of electrons, and followed by a gap, followed by another band, followed by another band. The upper two bands are really what determine the type of material that you're going to end up with, what type of solid you're going to end up with. Here is the situation. At the lower end of that is the so-called valence band, I should say. Okay, and then after that, the conduction band. This is filled. This could be partially filled or empty. Because if it's filled, then you have another band on top of it. That would be your conduction band. So there are several bands in here that I'm not showing. The gap in energy between the bands is what determines the type of material you have. If the Eg in this case is large and the conduction band is empty, then in this case there is no way under normal thermal agitations to have enough electrons in here to cause electrical conduction. This is usually typical of neutral, I'm sorry, not neutral, non-conducting, what do you call them? Insulating insulators. Okay, these materials, they don't conduct anything because they don't have any electrons under normal temperature. Even if you increase the temperature high enough, usually that's not enough for electrons to jump from the filled band to the conduction band. So in this case, this is a typical of that. Now at the opposite side of that is when Eg is small, or it doesn't matter, when the conduction band is partially filled, then in this case you have a conductor, because what this is the situation you have in here, you have a lot of electrons that are free to move, okay, in the conduction band, and in this case this doesn't matter then, okay. Then in this case, with a little bit of electric field, this will cause these electrons to move. So this is the case of conductors. Okay, there is a situation in between the two where you have the so-called semiconductors. In this case of the semiconductors, basically the gap is small between the valence band, and so this is Eg. And in this situation, under normal temperature, under low temperatures, this will be actually an insulator. When the temperature increases a little, or with something called doping, you can actually make the electrons available in here and move them to that side. So if you bring, for example, a donor of electrons and you place it just so that its energy level is just below this one, so it's going to give electrons actually, and those electrons will start doing the conduction. Because electrons are negatively charged, this type of doping is called an n-type doping. Okay. If you bring, on the other hand, acceptors, that they take electrons in this case, so you're going to move electrons again from the valence bond in this case. So what happened in this case, obviously, the impurity in this case at accept. So this is an acceptor. Usually has a very high mass, so it has high inertia. In addition to that, it's strongly bound to the host material. So in this case, it's not going to move at will. But the holes that is going to leave behind, so these are lack of electrons, sometimes called holes. Not sometimes, they are always called holes. So in this case, the holes are the ones that are going to be jumping in here, moving in the opposite direction where the others, resulting in the same current. So in this case, it's a positive, because a hole is a lack of electron, which is a positive charge. So we call this type of doping the p-type doping. Okay, we're going to come back in a minute or two to this idea for the semiconductors. And so in the first case, they were donors. But let me elaborate a little bit on metals, okay, because we really need to understand them. Because for the case of metals, we have a bunch of electrons now that are free to move. So one way of addressing, or at least talking about the electrons, is to think of them as some sort of a gas cloud that are free to move. And this provides actually another type of bonding called the metallic bonding. So this is the other bonding that exists in metals. Okay. In the case of the metallic bond, it's these electrons that don't belong to anybody, that belong to the community of basically atoms, that tend to provide stability also for the entire material in this case. So this is the metallic bond. Obviously, it's a lot weaker than the others, but that's actually there too. I mean, then some of them, depending on the energies, of course, okay, and the temperature. So here is the deal in the free electron model. Of metals, of course. So what you're assuming in here, we have a cloud of electrons that are free to move inside the material, inside the metal. So if we take, for example, a cubic metal, okay, block like this one of metal, and you have a bunch of electrons that are free to move. This is actually a problem that we dealt with before, and that problem is that of a free particle actually in a box, okay, in a cube in this case, okay, of length L. So if we go back into this previous chapter, actually, we will find that the energy in this case is expressed by 3 quantum numbers, and the 3 quantum numbers are nx, ny, and nz, and it's equal to nx squared plus ny squared plus nz squared times the constant, in this case is pi squared h bar squared over 2m times L squared. So this is the energy level for a given electron in this case, where nx and ny and nz are integers from 1, 2, 3, and so on and so forth. They cannot be 0, of course, okay, 4, and so on and so forth, okay, all positive integers, okay. Here is what we're going to define. We're going to define a density of states, because we have a bunch of them. Actually, we don't have just a single electron in here. So we have a bunch of them. So we're going to find in here, we're going to define dN as being simply equal to the density of states at a given energy level dE. In other words, GE is simply equal to dN over dE. So this is the density of states, okay. Here is how we're going to arrive to this expression. Each quantum number nx, ny, and nz, the combination of nx, ny, and nz give me a quantum number, give me a quantum state, okay? And each quantum state can have 2 electrons in it, positive 1/2 or a negative 1/2 integer, basically h bar, basically for the spin, because each electron can have a positive or negative 1/2 h bar. So basically that's how many electrons we're going to consider in here. So here is how we're going to think about it. Think of space in which the x-axis is actually nx, and the y-axis is actually ny, and the z-axis is actually nz, okay? And for a given point in space in here of these coordinates, did I put the correct coordinates? Yeah, that's correct. Okay, so even every given point in this space has coordinates that are expressed by this. This is a point of coordinates nx, ny, and nz. These are integers. This is basically an integer number in this case. Okay. So the radius of this sphere in here, because I'm considering all the states that are enclosed in this sphere. Okay. Again, I'm trying to get an expression for the density of states in here for a given quantum numbers nx, ny, and z for a certain number of electrons that are available for a certain metal. So the entire basically radius of this sphere of coordinates nx, ny, and z is going to be nx squared plus ny squared plus nz squared, the whole thing to the power 1/2. Basically, that is something that we can so this is just the radius of the sphere that has all of these numbers. All of them contain numbers anywhere between 1, 2, and 3, and 4, all the way to there. So it doesn't matter which number you're talking about. You have so many electrons that are already inside that one, and each and every one of them can be expressed its energy levels by this quantity in here, where n again changes from 1, 2, 3, 4, all the way to that number. Obviously, the volume of a sphere of this radius is 4 pi over 3 r cubed. So this is the volume of the sphere. Of radius r. Okay. The trouble with that is because nx, ny, and nz are equal to actually all of them are positive integers. So we cannot really consider the entire sphere, because the entire sphere is made up with this section, okay, plus another one on the other side, that's 2, plus another one on this side, that's 3, plus another one opposite to it, that's 4, but that's only half a dome. There is another side onto it in there, so the actual number of states in this case is going to be basically the actual volume of states in this case is going to be 1/8 of this number, because there are 8 of them. But you have 2 possible states for each electron, namely it can be in the state of positive 1/2 spin, or positive or negative 1/2 spin. So you really have to multiply this one to find the total. So this is the sphere, basically the size of the sphere that you have to consider is just pi over 3 r cubed. So in this case, because the 4 cancels the 4, so the actual dome contains this many electrons. Okay, electrons contained in this section of the sphere. I already accounted for the fact that I can have 2 electrons per quantum numbers, basically nx, ny, and z. Okay. Because one of them could still has a spin 1/2, and the other one of spin basically spin negative 1/2. So this is the actual number of electrons that I have in this case. Okay, so this is the number of electrons that I can have. That's the total number of electron states, I should say, electron states that I can have. Okay, of a given energy. Now I know what the energy is, so this is the energy actually is given by this expression. So E is given by, again, I'm going to write this in terms of the radius instead of nx and y. I've already defined it by the radius r. So this is r squared. This is this number nx plus ny plus times pi squared h bar squared divided by 2 ml squared. Okay. If we can get rid of this r and sub it in this expression, we will have an expression for n as a function of E, and from there we're going to have an expression for the density states, at least at absolute 0, at t equal to 0. Okay. So either way. Okay, so this expression will give me R equals to 3n over pi to the power 1/3. We're going to square this number and find the expression for E being equal to basically 3n over pi to the power 2. Is it to the power 1/2 or to the power 1/3? In here it's the power 1/3. So this is the power 2/3. Again, I took the cubic root of R in there, that's all. Times pi squared h bar squared divided by 2ml squared. Obviously we have some cancellations. I have pi to the power 2/3 and I have pi squared in here. Okay, it's probably more convenient to write the expression in terms of n as a function of E instead of E as a function of n, because that way we can take as the derivative of n with respect to. So we're going to take, so we should have done it the other way around, sorry. Okay, so let's find R from this expression and sub it in there, it's easier. Okay, so again, R from this expression, or R squared, is going to be equal to 2ml squared E over pi squared h bar squared. In other words, R is going to be equal to 2ml squared to the power 1/2 divided by pi h bar and then square root of E, or E to the power 1/2. Okay, now take this expression and cube it and we will have the n as a function of so n will be this expression times pi over 3. So we'll have pi over 3 times this expression, which is 2ml squared to the power 3/2 times E to the power 3/2 divided by pi cubed h bar cubed. Okay, when I take L squared to the power 3/2, that is L cubed, which is just the volume. So that is an important note in here. And then the matter of algebra in here to get, I will have pi h bar squared, then I have 2m to the power 3/2, then I have a 3 in there. So it's basically rewriting this expression in here. So n is going to be, cancel this with that, and I'm going to write it in terms of, so it's going to be 2m to the power 3/2 times the volume times E to the power 3/2 divided by 3 pi h bar squared. Okay. Okay. So what is this density of states? Just take the square root in this case, and we're in business. So when I take the, not the square root, take the take the derivative with respect to E. Remember, GE is dn over dE. So all we have to do is we have 3/2 that cancel that number, and this will be just to the power. So it's going to be 2m to the power 3/2 times v times square root of E. That's what I was saying, square root earlier. And the 3 cancels the 3, but I will be left with a 2 pi h bar squared, h bar cubed, I'm sorry. Okay. Did I forget a pi somewhere in here? Yeah, when we cube this quantity in here, this should be pi cubed. So this is pi cubed. Remember, we had to cube this quantity to find the volume in this case. So there is, when we cancel the pi and the pi cubed, we were left with a pi squared in here. And this is a pi squared. This is what is known in physics as chasing after pi. Basically, you do all kinds of calculations, and at the end of the day, basically, you're going to end up short either 1 pi or you have an extra pi. Okay, this is good actually for the density, but the actual distribution of the electrons in a given state is given by the distribution function Fe. So in a given number, in order to find really the actual number of the electrons, dN at a given point with respect to the energy. So we're going to take this GE times, again, a distribution that depends on temperature in this case. So this is the thermal distribution times, of course, due to the, because again, if we do think of this electron sitting in this cube as being basically frozen, basically there in temperature. This is how we're going to think about them. Well, the wrong assumption is to take Boltzmann-Maxwell distribution, because that will assume that all of the energies in this are given by that exponential. They are all in the ground state. Okay, give plus or minus basically 1/2, and that is not possible because they will have a lot of quantum numbers of the same type. So that is not correct. So we're going to use a different distribution where all of the electrons at t equal to 0 will fill the different ground states. Okay, they fill the first one, the second one, the third one, and so on and so forth until we run out of electrons. Then at that point there will be no more electrons higher than that point. So this is the energy E, and this is now the number of electrons, if you wish, as a function of the energy. So what we're saying in here in this case is there is a cutoff of energy which we're going to call the Fermi level, or the energy Fermi level. Okay. So when we do treat this problem with the statistics, we really need a different distribution than the Maxwell-Boltzmann distribution, and the one that corresponds to the fact that you cannot have more than one electron per state, and at the end you can have two, provided that their spins are opposite. So you're going to use the Fermi-Dirac distribution. And the Fermi-Dirac distribution gives you an energy distribution basically as a function of temperature, as being expressed by this expression, E minus this cutoff energy. This is at t equal to 0. At t equal to 0, usually you have the Fermi energy level for t equal to 0. But the one I'm writing right now is at any temperature. So, okay. So this will give me an idealization for the case of t equal to 0, but for any other t, it's going to give me this expression in here. So, where again, there is a cutoff. At higher energy, there will be no more electrons. At low energy, they are all going to be close from the ground state. And then due to thermal agitation, you have departures from both sides from the ground state. Okay. So this is basically how we're going to treat that. It is true usually for metals to treat the Fermi level, which is really where the cutoff happens in here, as equal to that with t equal to 0 Kelvin. Okay, so it's fine. You can treat that problem this way, but not for semiconductors. Not true for semiconductor. For semiconductor, the Fermi level depends really on the temperature. Okay. If we calculate the number of states now, okay, at t equal to 0. At t equal to 0, this function is very easy. It's equal to basically 1 in here for any energy level that's less than so this is the energy density. So I'm sorry, this is not n itself. Okay. Okay. So this is 1 below the cutoff for the energy is less than EF naught, and 0 above that. So if we calculate the number of electrons now in at t equal to 0 and integrate this expression with that function, basically with that distribution function, it's going to give me the number n. Okay, all you have to do is just go back to this expression. Okay, where you have GE, and GE depends on E, by the way, too. Okay, it has this dependency on E. So you're going to integrate it between 0 and infinity, knowing that f of E is equal to 0 anywhere after EF naught, and the integration is just therefore carried from 0 to basically EF naught. And if you do the calculation, you're going to find that the number of electrons in this case will correspond 2m to the power 3 halves, okay, divided by 3 pi squared h bar cubed, I'm sorry, this is coming from GE, times the ratio times pi to the power 4/3 times, what is it, another, I'm sorry, what am I writing in here? No, that's not correct, okay, times just the EF to the power 3 halves now. Okay, basically you take the entire derivative of this expression in here, okay? I think I've forgotten the number n, the volume v somewhere in there, okay? So you need v in here. So when you take the entire derivative of this expression, we're going to go back into this n, except that it's evaluated up to EF, basically, okay? So there is a v in here. As a matter of fact, you could express EF now as a function of n, and it's going to be as a function of n over v, actually, because you have an n in here, you have a v in there, and the whole thing is to the power 2/3. So if we are careful enough to do that, and we're going to do EF, then the Fermi, this is the Fermi level. So if you're wondering how much is it, and this is actually important for your homework problems, divided by 2m, which is to the power 3 halves. Now it's when you invert it, it's going to go away. And now times 3 to the power 2/3, I'm sorry, pi to the power 4/3, because you have 2 times 2, that's 4 divided by 3, that's 4/3. And now you have h bar, okay? H bar squared, because you have h bar to the power 3 times 2/3, it's going to be left with an h bar squared, times n over v, because you have an n in here and you have a v in here, to the power 2/3. So just reworking this expression to find out the energy level in terms of n over v, and n over v is actually the number of charge carriers, the number of electrons, free electrons per unit volume. Number of free electrons per unit volume. Sometimes we write it as n. I really didn't want to write it as n, but when we did chapter 25, we expressed this one as the density of carriers, and this is the symbol we used for it then, which is n equals to n over v, so that's the number of free electrons per. So you could express this one, so this is a direct correlation between the Fermi level and the number of free electrons, or the charge carriers per unit volume. So this is an important one. M, of course, usually is the mass of the electron, and h bar in this case is just a constant. So this is the only thing that matters in terms of the different materials that you have in here. So this is actually what you're going to be needing for your homework problem. You can calculate the average energy, and basically you integrate the actual expression in here. Again, you can do it at t equal to 0, which is easy because the function is 1 below EF naught and 0 above. So you can find that the average energy, of course, you have to multiply by E, and you integrate from 0 to infinity. So it's going to be E times GE times f of E dE, and you integrate again from 0 to infinity. This is what we're going to define as E average. If you do the calculation again, because all you're going to end up with is another power of E that is going to come into the expression. So we have e to the power 1/2. Now we're going to have e to the power 3/2, and you carry the calculation. You're going to end up with an expression basically of 3/5 of EF naught. Okay, again, this is at t equal to 0. If it's not 0, the calculations are a little bit complicated actually, and you really need to have a numerical calculator because of this f of e now that depends on temperature, and the problem becomes a little bit more complicated. I'm going to go back into a little bit of the semiconductors. In semiconductors, the case that I'm going to consider is the p-n junction. Okay, so you have on one side the p-type material, and you have on the other side is an n material. And when you do connect the two, of course you cannot connect them after you make them, you have to connect them during their making, actually the position of the materials on plates of the other. So now what happened initially is that the excess of electron will start to recombine in here with the excess of holes on the other side, or lack thereof of electrons in here, and you will have a region in here that starts to develop. This was neutral to begin with, so now you're going to end up with charges in here that are going to be left positive in here and negative on this side. So an electric field now starts to form this way, and that electric field now will prevent further migration of electrons. Okay, so at some point you will have, so there will be a zone in here that has already its voltage. Now, depending on which way you connect the circuit, if you connect it so that the battery is looking like this now, okay. So what's going on in this case is the charges will come in here, which is positive charge. They will combine with this negative charge, and now you can continuously push these charges on the other side. Usually it's the electrons. I mean, you know that from physics too, basically, that the electrons will come in here, recombine, and in doing so they are going to basically cancel that charge, and the current will actually flow no problem. But if you do it in the opposite direction, that is not going to work at all. Actually, it's going to be acting as an open circuit in the opposite direction, because all you're trying to do is build more stress on this already existing field by pushing more positive charges on this side and negative charges on the other side, and that is going to lead to the current not moving in there. As a matter of fact, the way I'm describing it looks like it's linear. It is not. As a matter of fact, if you do the analysis, the dependency of the current on the voltage is a little bit more complicated and involves a saturation current, and that saturation current is what I was describing earlier. As a matter of fact, that the picture I described as a static picture is not, because at any given point there is actually a destruction in this zone of the ions, but there is also it's called a recombination in this case, but in this case it's being supplied also by thermal agitations, formation thermal agitation. So this is the voltage in there. I mean the current that is, the voltage that's going to establish itself in there. So if you do an analysis, you're going to find that at any given point that this actually depends on the temperature and depends on the voltage itself. So it's E times V, the voltage that is applied in here actually, divided by kBT. Minus 1. Okay, so this is the expression that sometimes is called Shockley equation, that gives me a nonlinear dependency of the current versus the voltage. We were used to V equal to Ri. This is not anywhere near that. Okay, so the current and the voltage are not proportional to one another. Actually, there is that exponential in there. Okay, this is your chapter in a nutshell. Hopefully I'm going to post some problems from this chapter, and we'll have a discussion on these problems and how to do them, and that's for chapter 42. Thank you.